Hello everyone, my name is Caden Plew, and I'm looking forward to presenting this work for you today, which is titled Transient Thermal Performance of High Temperature Particle Storage Bins, and is a collaboration between the University of Texas at Austin, where I'm currently a graduate student under Maggie Chen, and Sandia National Laboratories, where we are working with Jeremy Sment, Mario Martinez, and Clifford Ho. The main foundation of the work being presented here is an ongoing effort by Sandia National Laboratories Solar Energy Group to develop the Generation 3 Particle Pilot Plant, which is a concentrated solar plant that uses a high-temperature particle circulatory system to transfer solar energy potential to a high-temperature supercritical CO2 Brayton cycle. And the prototype system is expected to have a 1 megawatt thermal duty, 6 megawatt hours of thermal storage capacity, and a levelized cost of electricity of 6 cents. Now, central to the high-temperature particle circulatory system is the high-temperature particle storage bin, which is a regulatory mechanism for the temperature and the flow rates throughout the system. So it's these high-temperature particle storage bins that are going to be the focus of this work, and our primary target is to be able to maintain reliable flow through the storage bin and to be able to predict the outlet temperature as a function of conditions throughout the rest of the system. Okay, and when we're focusing on these bins, there are two geometries that we consider. The first is the mass flow bin geometry that's shown here, and it induces a simple uniform translational motion from the top to bottom. And you can see that in the video that I'll play here.
The use of
and when the particles start to move, they're colored in this tan and gray color just to show the propagation of the flow. And you can see when it starts to move, those particles are just shifting uniformly downwards, and then once they hit the cone, they start to mix a little bit. Okay, and so the second geometry that we consider is called the funnel flow geometry, which is shaped such that it induces a more complex flow where you have this center flow channel develop. And on the top surface, you have particles translating from the outside radially inward, converging at the center, and then moving down that center flow channel. And you can see that again in this video that I'll play. Again, the particles are colored differently just to show the propagation. And you can see here the center channel developing, the particles moving across that top surface, converging in the center and then flowing downwards. And you can also see the regions that are stagnant in this domain. The main contribution of this work is the direct comparison of the thermal modes that occur in the funnel flow bins versus the mass flow bins. And we'll get into why that's important for the G3P3 system in particular, but this is also a significant step forward for solar engineering in general, because as we move towards operating systems at higher and higher temperatures, we'll need to consider using fluids such as the particle system that's shown here that can reach those high temperatures without undergoing a phase change. Okay, so for the G3P3 system in particular, understanding these thermal modes to a degree that allows us to predict and forecast the cyclic behavior of the system is crucial in allowing us to forecast for dispatching purposes, as well as being able to apply control algorithms at different operational levels. So I'm going to briefly go over our approach to modeling both the funnel flow and the mass flow processes, and then we'll get into the direct comparison between the thermal transients in the funnel flow versus the mass flow regimes. So instead of taking the approach of actually modeling the 2D momentum equations coupled with the energy equation, we're actually taking an approach where we separate the domains into multiple simpler domains that can be solved in a more straightforward way. And we do that by approximating different domains in the flow based on what we know about it, kind of by looking at the flow regimes, such as how we saw with the videos earlier. So for the funnel flow process, we start by looking at the top flow surface, which is essentially just a flowing surface that's flowing inwards radially and converging in the center. Now we approximate this as a plug flow to simplify the equations and solution, and then we solve the associated energy equation, which has a semi-analytic numerical solution. And it's a similar case for the center flow channel, where we're approximating this as plug flow, and then again solving the energy equation based on the velocity there, and the advection and diffusion that occur throughout that flow channel. Okay, but note here that both of those solutions are dependent on the boundary with the stagnant region. Okay, so this is where this third solution comes into play, where we derive a heat kernel for the stagnant region, which is essentially used to tell us how the stagnant region, how the temperature profile in the stagnant region is affected by each of the boundary conditions as well as the initial conditions. So that's what this notation means here. The heat kernel tells us the effect of any impulse coming from the boundary. Once we have this heat kernel, we use it in this equation to derive our temperature solution, which is essentially just a combination of the contributions from the initial condition and each of the four boundary conditions, which is what allows us to couple the stagnant region with the center flow channel, the top flow channel, as well as the boundaries that connect it to the exterior environment. So we use the same approach for solving for the temperature distribution in the mass flow bin, where we start here by deriving the heat kernel for the cylindrical region in the mass flow bin, because we can assume that that is just a body of particles translating uniformly downwards in the cylindrical region, as we saw in the video that we showed in the previous slide. So again, this heat kernel that we derive here is just a function that tells us how the temperature inside of this cylindrical region is affected by each of the boundary conditions and the initial condition. So we use that in the same kind of equation, where we get the temperature distribution as a function of the initial condition and each of the four boundary conditions. Then we solve for the temperature distribution in the flow cone, where we're assuming just a 1D profile to simplify the process, where we account for whatever particles are flowing in, whatever particles are flowing out, and the heat loss to the environment through the exterior of the cone. And this comes out to be a solution to just a basic energy equation, which has a semi-analytic numerical solution. Here I have results that compare a simulation for a mass flow bin versus a funnel flow bin. And in both bins, they started with the same amount of mass and they have the same flow rates, which allows us to do kind of a direct comparison. And here we're mainly focusing on the outlet temperature, which is plotted up here on the left. And in the paper, you'll find a more rigorous comparison and validation to experimental data and other modeling efforts that we've undergone. So let me play this video and then I'll kind of walk through what's going on here. So the funnel flow bin is in the center and then the mass flow is on the right. Let me pause this and point out the first distinction, which is that the outlet temperature in the mass flow bin immediately starts to drop, compared to the funnel flow bin, which kind of has a lead-in period where the outlet temperature is constant until you can see this region of cooler particles being advected downwards through the center flow channel. And that outlet temperature stays constant until those colder particles are advected all the way to the bottom. When that propagation reaches the bottom, the temperature starts to drop, then kind of drops from there and eventually actually meets up with the outlet temperature of the mass flow bin. So you can see how having an understanding of these thermal transients is hugely important for both the design and operation of the high temperature particle circulatory system, as well as the entire CSP system at large. And with that, I'm going to stop the presentation here. I was really happy to have the opportunity to share this with all of you, and I really look forward to answering your questions and any discussion that occurs in the future.